Dear students, now we are going to learn the angle of arrival estimation. So in the propagation channel, even for one source, there are many possible propagation paths and angle of arrival. If several transmitters are operating simultaneously, each source potentially creates many multipath components at the receiver. Therefore, it is important for a receiver array to be able to estimate the angles of arrival in order to decipher which emitters are present and what are the possible angle location. This information can be used to eliminate or combine signals for greater fidelity, suppress interference, or both. The next thing is the angle of arrival estimation has also been known as spectral estimation or direction of arrival estimation or bearing estimation. So, what is this angle of arrival estimation is? So, when we are keeping the transmitter and the receiver, if it is the direct line of sight, then the arrival of signal is in the straight line. Similar way, we are going to estimate the angle of arrival estimation in multipath signals. So some of the earliest references refer to spectral estimation as the ability to select various frequency components of collection of signal. So that is the purpose of this estimation to select the various frequency component out of collection of signal. So we need to estimate this angle of arrival. Here, this bearing estimation is a term more commonly used in the sonar community and is the angle of arrival estimation for acoustics problems. So mainly they are using this in the sonar community problems and also in the acoustic problem. Much of the state of the art in the angle of arrival estimation has its roots in time series analysis, spectrum analysis, and periodogram, eigenstructure method, parametric method, linear prediction method, beam forming, array processing, and adaptive array methods. So, in that angle of arrival estimation, we are going to define some parameter as following. So now see here, we are first thing we are going to discuss of fundamentals of matrix algebra. In that, see here. So these types of vector basics already we have learned in some subjects also. So now we are going to analyze for antenna design. So the first thing is column vector. The vector A bar can be denoted as column vector as a row vector. So if the A is the column vector or single column matrix, it can be described as like column wise you have to represent A1, A2 up to AN. Similarly, for the row vector, if you are taking the B is the row vector or single row matrix, it can be described as B is equal to B1, B2 and Bn. And now the next parameter is vector transpose. So any column vector can be changed into a row vector or any row vector can be changed into column vector by the transpose operation. The next thing is vector Hermitian transpose. The Hermitian transpose is the conjugate transpose of a vector denoted by the operator H. So thus the Hermitian transpose of A bar above can be demonstrated as, so here that A1 conjugate up to AM conjugate. So this is the format of vector Hermitian transpose. The next thing is vector dot product. The dot product of the row vector with itself traditionally given by B dot Bt. So now the B1, B2, Bn. So it will be multiplied by the column vector B1, B2 up to Bn. So by that we will get the value is B1 square plus B2 square plus Bn square. The next thing is van der Mouding vector. So what is this van der Mouding vector means? This is the m element vector such that see here x power 0 the array vector steering here this van der Mould vector is nothing but this is a steering vector. That means array steering vector. So how you are steering this matrix means based on your m element value. So here you have to substitute the m value from 0 to m minus 1. So based on that, we can select this Vandermonde vector. So now the next thing is matrix basis is this I think might known everything. So that size of the matrix, how we will define m cross n. Similarly, the matrix determinant we will calculate in that basic classes also. Thank you.